Okay, so we are in the first week and our first lecture in this course, mechanics of solids. So, in this course, we are going to study how different materials deform and respond under the action of some external loading. So, if you consider a body, say this is a body, it has some supports and it is exposed to some kind of external loading. There may be internal loading also, but for the time being let us consider some external loading. Now, under the action of these forces, say this is a phi, obviously this body is going to deform. If the body deforms, then there will be stresses and strains developed inside the body. So, in this course we are going to investigate how under the action of this external force, say phi in this case, the stress is developed inside the body, say sigma I, or some strain is developed inside the body. So, this is a branch of applied mechanics that actually tells us how a body deforms. So, how a body deforms. That means, we have a body which may deform, but which may not. So, if it deforms, we call it a deformable body. If it does not, then we call it a rigid body. Right. Now, in engineering, if we just take an example, say we have a beam. And then we apply a point load at the middle, say P. Obviously, under the action of this point load, this beam is going to deform in this manner. Obviously, you know what is the deformation at the center. Now, the moment it deforms, there is a change in dimension, and the moment there is a change in dimension, obviously, there will be some strain developed inside the body, and that will be manifested in terms of stresses also, right. So, we will quantify these stresses and strains that develops within the body. Now, obviously, in our entire course we will not consider any rigid body motion, and our entire attention will be focused on this deformable body. Now, the deformable body can actually deform following different pattern. In some of the cases, for example, in this case of a beam, the moment we apply the load, it deforms, and if we withdraw this load P, obviously, this beam will come back to its original position. Now, if we increase this load and keep on increasing, what will happen? At some point of time, the moment we apply this load, then there will be a permanent deformation. And after that, if we remove the load, this beam is not going to come back to its original position. So, if you look at that pattern of deformation and also the loading, then we can actually subgroup these deformable solids into two major classes. One is called elastic and then plastic. In case of elastic, the moment you withdraw the load, the body will come back to its original position. But the moment there is a plastic deformation, so it will not come back to its original position, but will take a new shape. And in this course, we are going to study only elastic deformation. Now, there are different examples in civil engineering. For example, we take say beam, column, then slab. These are the different examples of elastic body. Obviously, the same body under the action of a different loading pattern may behave in a manner that there is a permanent deformation, or otherwise it is a plastic deformation, but our entire discussion will remain within the domain of elastic deformation. So, let us consider a prismatic bar to start with. So, we have a bar and then we apply a force P at the end. Now, the total length of this bar is L, and let the diameter of the bar be D, and we apply a force of P. The cross section of the bar is equal to say A. Now, the moment we apply this tensile force, so it will cause an elongation in the bar, and say this amount of elongation be delta L. Now, all of you know that stress developed because of the action of this force P over a cross sectional area of A is P by A. And also the strain is change in length per unit length. So, the stress that we get here due to this force P, a tensile force, this we call normal stress. Similarly, the strain we call it normal strain. Now, if you look at the definition of strain, so it is the change in length per unit length. Now, in this definition, we have considered the initial length. Now, if we consider the initial length when we calculate the strain we get is called nominal strain. Now, instead of this L, we can consider the complete length. So, that means from this point to this point, and then we can redefine strain using the gauge length after we apply the force P. So, if we use the actual distance between the two opposite faces, then the strain we get is called true strain. Sometimes we also call it natural strain. but mostly we deal with this nominal strain, where we use the initial gauge length as the length over which the deformation is evaluated. So, obviously, what we have in this case is stress developed inside the body due to the action of this force. Now, in this example we have tensile force, we can have compressive force as well. Now, you all know that stress is proportional to strain over a loading range, obviously, and stress by strain is called Young's modulus, E. So, this is the material property. Obviously, in this example our material is homogeneous. So, what we have learned is that this body, this prismatic bar, it is a elastic body, and the moment we apply a force of P at the two ends, this body deforms because we apply a tensile force. There is a elongation in the body by a amount of delta L, and then we can consider the initial length, the gauge length, as the distance between the two opposite faces, and then use that to evaluate the strain. Then we get the nominal strain. Now, for a material, if the stress is proportional to strain, this behavior we call it the linear elastic behavior. So, if we plot stress versus strain, obviously it will be a straight line over the initial range. Right now, we are not going beyond certain limit. Obviously, as we progress in this course, we will go beyond this linear limit and we will see how it behaves. So, what we have defined is that the material may deform elastically or plastically, but in both the cases, the moment we apply some external force, there will be internal deformation, and the moment there is an internal deformation, that will develop strain and subsequently stress. And in fact, when you go to design this structure, for example, say this beam, so under the action of this load P, what we do at different sections, we evaluate how much stress is developed, and then we select a material, so that the material along with the cross section of the beam, it can withstand that applied stress. So, that is the basic philosophy of design, and that is the reason it is also important to evaluate the internal stress and strain when we apply some force on a elastic body. Now, if we just look at the stress strain behavior of different material, then we will see how different material deforms under the action of external forces. So, stress versus strain. Now, obviously, we are going to take a material which deforms elastically. Say we consider steel. And And if we plot the stress strain behavior of this material, we initially get a linear deformation because of the elastic nature, and then it starts deforming. So, initially stress is proportional to strain, and then if we apply more force, then it deforms in a different way, and we get first a valley region, and then what happens beyond this point, as we increase the force, we get a pattern like this, and then finally at this point the material fails. Now, if we mark different points on this curve, so what we have here, say this is A, then this point is B, then this point is C, then D, and finally this is E. So, we have on the x axis different strain ranges. Let me first mark and then I will explain how the material behaves. So, this is say A prime, B prime, C prime, D prime and E prime. Now, this initial range, this is the linear region. Once it crosses linear region, then we have perfectly plastic region, then if you look at this path C to D, what happens if we increase the force, it moves along the path C to D, and this region is called strain hardening. And then finally, this is the region, it is called necking. I will explain that in a minute. Now, if we draw the horizontal lines at this point, so we get different stress point. So, this is the proportional limit . Why it is called proportional limit? Because up to this point stress is proportional to strain. So, if we apply a force, then the body will deform following this path, and if we go for unloading, it will again come back to 0. Now, this point is called yield stress, because beyond this point permanent yielding occurs, and then the stress at this point, this is called ultimate stress. Now, how do we develop this stress strain curve? So, what we do, we take a prismatic bar, then we apply a tensile force at the ends using a machine called UTM, universal testing machine. There we mark this gauge length, and obviously we consider this initial gauge length as the length that we will use for strain evaluation. Now, beyond this point D, what happens at the middle, due to the elongation, the beam or the prismatic bar deforms in this way. So, there is a change in cross section and this phenomenon is called necking. Now, if we measure this exact dimension and at this point, if we calculate P by A with the exact dimension while we evaluate the cross section, then instead of this path, it will actually move like this, because this necking phenomenon, the diameter D, it is going to decrease, and because of that cross sectional area reduces and therefore, the stress which is P by A, that increases. So, instead of this E, we get say this new point if we consider necking. Now, the material that deforms in this way, we call it ductile material. Ductile material, before they reach the ultimate stress, they deform by a significant amount. Steel is a ductile material. It has basically iron plus some amount of carbon, very small amount. Now, depending upon the proportion of carbon, the ductile property of this material varies. Now, if we increase the amount of carbon, then this material will behave in a completely different way, and then we call it a brittle material. So, depending upon the stress strain behavior, material can be of two types, ductile or brittle. Now, for brittle material, if we plot the stress strain curve, how it will look like? Initially again, there will be a range where it will have proportional limit, and then as we increase the load at some point, the material fails. So, this is again the proportional limit, and beyond this the material does not behave linearly, and then it follows this type of typical stress strain path. For this type of material, because we do not have perfect yield point, so what we do, we identify 0.2% strain, and then we draw a line parallel to the initial part and then that point we identify as the yield point. So, this is 0.2% offset that gives us the yield point. So, if I just sum it up, what we have learned is that different bodies, they deform under the action of external loading in a different way. It may be a rigid body, it may be a deformable body. The deformable body can be classified into again two groups. It may be elastic, it may be plastic. For elastic, we will quantify the stress and strain as we apply some external force, and we will see what are the different components of strains, what are the different components of stresses, and then how they are interrelated. So, with that, let us close our first lecture here. We will continue on this topic in the next class. Thank you.